In this video, we are going to sketch the curve of y is equal to x plus 3 all over x plus 1. Now you can see that this is a rational curve because it has a numerator and a denominator in the expression of the function. The first thing that I'm always going to look at are the asymptotes. So if I want to find the asymptotes of the curve, I need to find, is there going to be a vertical asymptote, a horizontal asymptote, or an oblique asymptote? As I definitely have a factor in the denominator that could not be cancelled out, I cannot have x plus 1 equals 0 because that would give me an undefined denominator. In other words, I am definitely going to have a vertical asymptote when x is equal to minus 1. The next thing that I notice is that the degree of the variable in the denominator is equal to the degree of the variable in the numerator. And that means that I should be able to find a horizontal asymptote by looking at the limit as x tends to infinity. So you'll remember that if I do the limit as x tends to infinity, I divide both the numerator terms and the denominator terms by the highest degree of x that I found in the denominator. So in the numerator, I'm now going to have x all divided by x and plus 3 all divided by x. In the denominator, I have x divided by x and I have 1 all divided by x. In the numerator, x divided by x is 1, as it is in the denominator. And the second terms, both in the numerator and the denominator, both tend to 0. In other words, the limit as x tends to infinity is going to be a limit of 1. That means that I have definitely got a horizontal asymptote, and the horizontal asymptote is going to be when y is equal to 1. As this fraction is not an improper fraction, in other words, it's not top-heavy, there will not be an oblique asymptote. The next thing that I need to look at are my stationary points. Now, if I want to find the stationary points, I must find the derivative of the function y in the variable x and make that equal to 0. Now, the function is a quotient, and so I'm going to have to use the quotient rule in order to find the derivative. If I name the numerator of my function the function f and the denominator g, I can now easily find the derivative. Remember that when I find the derivative using the quotient rule, I start by saying, what is the derivative of f? And times that by g. And then minus. What is the derivative of g? And times that by f. And I must write that all over the function of g all squared. So that's going to be over x plus 1 all squared. If I simplify this, this is going to be that the derivative is going to be given to me as x minus x is 0, and then 1 minus 3 is minus 2. So lastly, I have minus 2 all over x plus 1 squared. Now remember, I said to you that if I had turning points, then the derivative, which is the gradient of the tangent at that point, would be 0. If the derivative is equal to 0, it means that minus 2 all over x plus 1 squared is equal to 0. Well, this means that if I try to solve this equation, I would get that minus 2 is equal to 0. Clearly, this is impossible. So this means that there is no turning point on this curve. As I found that the graph has no turning point, I need to find the gradient of the curve. As it can't turn, it must all be decreasing or all be increasing. Now you'll remember that I've got the gradient test or the concavity test, and I could use either. But as I already have my first derivative, I'm going to use the gradient test. We discovered when we found our asymptotes that there was one value that x could not be, and that was when x was minus 1. If I know that x can't be minus 1, then I'm going to choose a value just to the left of it. Let's choose minus 2, and just to the right of it. And I'm going to check and see what is the derivative going to be when x is minus 2, and what is the derivative going to be when x is 0. By substituting these x values into the derivative formula that I found was minus 2 over x plus 1 all squared, I find that on the left, I have a negative answer, which means that I'm going to have a decreasing gradient. On the right, I also get a negative answer, which means that my graph remains decreasing. Let's see what else I need to find. I haven't found a y-intercept or an x-intercept, and I'm going to see if I can find these next. My y-intercept is when x is 0. So if I make x 0 in the original function, I'm going to get 3 over 1. So the y-intercept is going to be 0, 3. The x-intercepts are when y is 0. And if I solve, I find that I get only one x-intercept, and that is going to be at minus 3, 0. All that remains now is for me to take this information and to plot it so that I can find the diagram which represents this function. Whenever I draw a curve, the first thing that I always put in are my asymptotes. Remember, I had two asymptotes. We found that there was a vertical asymptote when x was minus 1. We said there was a horizontal asymptote exactly when y was 1. We also plotted two critical values. That was the y-intercept at 0, 3 and the x-intercept at minus 3, 0. Lastly, my graph has to tend towards these asymptotes, but the gradient must be decreasing. The only way that I could do this was filling in my graph in quadrant 1 and quadrant 3. You might have done the second derivative test. In other words, you would have found that in quadrant 1, your graph would have been concave up, and in quadrant 3, your graph would have been concave down. We have now drawn the graph of y equals x plus 3 all over x plus 1.